Hello students, it is lecture 3 of classical mechanics. In the last class we did questions on degree of freedom. Okay, so today we will learn about constraint. We will see what are the different types of constraint and some questions related to constraint and general definitions which are important for classical mechanics. Okay, now first of all, constraint. Constraint are basically condition between coordinates or the relation between coordinates. The simple definition of a constraint is basically a relation between the coordinates. Okay. In mechanics, constant relation is geometrical relation between coordinates. Whenever we talk about mechanics, under mechanics, whatever the constant are, these are basically the geometrical relations. Okay, now here is written one example. Gibbs-Duhem relation serves as constant relation in thermodynamics. When we will study thermodynamics, we will discuss about it. That Gibbs-Duhem relation is also considered as a constraint in thermodynamics. But for mechanics, what are the common constant equation? These are basically geometric relation. Okay, example, the double pendulum oscillating in a fixed vertical plane. It is a double pendulum oscillating in a fixed vertical plane. Okay, it's the first pendulum and it's the second one. Let this be origin 0 0. The coordinate of this be x1 y1 and the coordinate of this bob is x2 and y2. Okay, let this length be L1, which is a constant fixed value, L2 constant fixed value. The angle created by the normal is theta 1 and theta 2. Okay, now whenever we use the distance formula for this relation, for this particular figure, what do we get? X1 square plus y1 square is equal to L1 square, distance formula, right? Now if we calculate the distance between these two, x2 minus x1 square plus y2 minus y1 square is equal to L2 square, right? For this system, the number of constant equation we have here is 2, right? The constant relation or constant equation. These are two constant equations. Now what is the number of variables used? Number of variables used x1, y1, x2 and y2, that is 4. Okay, so what do we get from here? The degree of freedom is number of variables minus number of constant equation, as we already know as per our previous videos. So degree of freedom is equal to 4 minus 2, that is 2. So the degree of freedom for a double pendulum is 2. It has two constant equations. Okay, now for the same case we can see, if we would have chosen theta 1 and theta 2, the angles, they would have been like independent generalized coordinate. Okay, and if we are choosing x1, x2, y1 and y2, it is dependent generalized coordinates. Okay, the next thing we're going to discuss is the classification of constant. See, constants are of various types, like it has many types in it. So the very first type of constant is holonomic constant. If the constant relation is expressed as algebraic equation or integrable or solvable differential equation, then it is holonomic constraints. Yeah. So what is a holonomic constant? Holonomic constant are the one in which the holonomic equation, the constant relation we are having, it is in the form of algebraic equation or solvable differential equation or integrable differential equation. We need to know there are various type of differential equations. Some of them cannot be solved. Okay, if the constant equation is in such form, then it is non-holonomic. Okay, so what is a holonomic constant? Holonomic constant is the one if the constant relation given is expressed in the form of algebraic equation or integrable or solvable differential equation. Example, previous example of double pendulum. We solved here the question of double pendulum. In this question we can see these two relations which are given. These are basic algebraic relation. Okay, so since it is a basic algebraic relation, then it is holonomic constant. Okay, the constant here mentioned is holonomic. The next is, see, we have discussed this question in the previous lecture. Okay, x and y coordinate are here. It's a triangular block which is moving, which was moving, and the square block was sliding over it. Now if the setup is stationary, we consider this point. Okay, take it as x distance, this is as y distance, and we are taking this, the last point of that triangle, as x1. Okay, so this distance will be x1 minus x, correct? And this point we took it as y. So for theta, we write tan theta is equal to y upon x1 minus x. Okay, therefore y is equal to tan theta x1 minus x. Now this theta is a constant because the triangular block showed here is a fixed solid figure, right? So this theta do not change, hence the number of variables here is 3. The equation or the relation between them is 1. So degree of freedom of this setup will be 3 minus 1, that is 2. Now the relation which we see here, y is equal to tan theta x1 minus x, it is basically a common algebraic equation, right? Since it is a common algebraic relation or common algebraic equation, therefore it is holonomic. Now the next example is constant equation of x dy plus y x dx, it is the constant equation x dx plus y dy is equal to 0. It is a common differential common equation, and on solving it, it is highly integrable, hence it is holonomic. Another relation, for example, is f1, which is a function of x and y dx, plus f2 x comma y dy is equal to 0, where f1 and f2 are non-solvable. Then this relation is non-holonomic, or this constant relation is non-holonomic. Okay, now we will discuss non-holonomic equations more clearly. Now what is a non-holonomic constant? The constant relation is not an algebraic equation. Okay, it may be an inequality or non-solvable differential equation. Now what is the case for non-holonomic constant? The case for non-holonomic constant is when the constant relation is not an algebraic equation, means the equation that is given here is not an algebraic equation. It can be an inequality or it can be a non-solvable differential equation. For example, it is a board. Okay, it is a triangular board. We just drawn x and y coordinate onto it. Now there is a coin or ball or whatever, like they can be, like this is a coin. Okay, the coordinate of the coin is x and y. Now is there a relation existing between this x, y and a? The only relation they have here is x is less than equal to 0, sorry, x is greater than equal to 0 and less than equal to a. Okay, means x lies between 0 and a. Similarly, y lies between 0 and a. That's it. And what is this? These are the inequality, and since it is an inequality, therefore it is non-holonomic. Okay, non-holonomic constant. Confinement of a coin inside carom board is non-holonomic constant, which is the same statement, I would say. Now the other example is, suppose here is a sphere, okay, and there is a point r. This r point denotes a fly. Okay, so this r will always lie between the zeroth point, the centermost point, and the boundary. Okay, So the inequality for the sphere for the fly will be 0 greater than equal to r greater than equal to capital R. Okay, since it is an inequality relation, inequality constant relation, therefore it is non-holonomic constant. Now, holonomic constant reduces degree of freedom. Non-holonomic constant does not reduce degree of freedom. We wrote one example, like we solved one question over here. Yeah, we can see here. Degree of freedom is equal to number of variable minus number of constant equation. Okay, the word equation is used only in the case of holonomic equations, because whenever we talk about non-holonomic, these are not considered. Okay, not considered as in like they are not used in this formula. Okay, this formula is made for holonomic equations. Okay, no relation, nothing, just holonomic equations. Now that's why the statement is mentioned here. The holonomic constant reduces degree of freedom, while non-holonomic constant does not reduce degree of freedom. The next type of constant is scleronomic. Scleronomic constants are the one which not explicitly dependent on time, which do not depends on time. Okay, and rheonomic constant are the one which explicitly depends on time. Okay, in all previous example the constant is scleronomic, because we can see each of these examples we do not see the presence of time. Like we go for double pendulum, no presence of time in the equation. We go for this relation, this solid block, no presence of time. These all are scleronomic. Okay, now whenever we talk about this system, it is holonomic and scleronomic. Scleronomic because there is no presence, no dependency of time. Okay, now other example here shown for rheonomic. XYZ coordinates are made. This is a sphere. There is a particle on the sphere and this sphere is expanding. Okay, if the sphere is expanding, it means the particle will also get away from the center, right? So let v be constant, means the rate of expansion, let that be constant. Okay, so the relation we get here is small r, that is this thing from the particle, will be equal to capital R plus Vt. T be 0 at the initial point. As soon as time passes on, it goes far and far and far. This constant relation is holonomic. First thing, it is common equation. Second, it is rheonomic. Rheonomic because there is presence of time in this relation, dependency of time in this relation. Now, important terminology used in classical mechanics. The first thing, generalized coordinate, QI. We denote the coordinate, generalized coordinate as QI. Okay, QI denoting the number like Q1, Q2, Q3, etc. And the basic definition of them will be a suitable variable, whatever we choose. Generalized velocity, that is QI with a dot above it. This dot denotes like derivative of t, the total time derivative of generalized coordinate. Okay, now what is the example of these? Like we have written here QI and QI dot. If we take generalized coordinate as linear coordinate, we get QI dot as linear velocity. If we take angular coordinate, we get angular velocity. If we take charge, we get current. If we take linear momentum as generalized coordinate, we get force as generalized velocity. And if we take angular momentum, we get torque. Okay, the next topic that we will study, like the next definition we will study here, which we will be going further into classical mechanics, is Lagrangian. Now, Lagrangian is a suitable function which is used to describe the dynamics of a system using Euler-Lagrange equation or formula. First thing, we design this function. Second, it does not have any physical meaning. Third, it is not unique. Means for one system we can introduce many Lagrangian, okay, or we can introduce or we can construct many Lagrangian. The very first thing, it is a suitable function. What is Lagrangian? It is a function, okay, a function which is used to describe the dynamics of a system using Euler-Lagrangian equation. We will study this in detail later on, okay. We are the one who's designing it. It is not having any physical significance or physical meaning, and it is not unique, okay. You can have n Lagrangian for a system. It depends on you how you are like quoting it. For example, here is a block attached with a spring with a wall. Now for this setup, the Lagrangian is L is equal to 1 upon 2m x naught square minus half kx square, which is generally the kinetic energy minus potential energy, okay. Similarly, if we take this setup, LC circuit, okay, for this circuit the Lagrangian is defined as half L q dot square minus q square upon 2c, okay. So this equation shows that it is not always compulsory that Lagrangian is kinetic energy minus potential energy. There are various forms which we will see, and it depends on us how we are using it, okay. And this sign is called tilde, okay. Lagrangian, that is L tilde, is half L q dot square minus q square upon 2c. The next is let there is a free relativistic particle whose rest mass is m naught and moving with v velocity. So its Lagrangian is described as minus m naught c square under root 1 minus v square upon c square. See, we all know for relativistic particle the kinetic energy is m naught c square upon under root 1 minus v square upon c square minus m naught c square, and its potential energy is 0 for free particle. So if there would have been like kinetic energy minus potential energy, this thing would not have been possible. Therefore it is shown here again that choosing Lagrangian is on us. We are the one who are constructing Lagrangians with respect to the solution, with respect to the needs, okay. Lagrangian is defined differently, like it is defined differently with respect to the condition, with respect to the question, etc, etc, okay. Mostly Lagrangian is basically function of qi dot and t, that is generalized coordinate, generalized velocity and time. But in some cases it will also be a function of L, which is L is a function of qi dot, qi double dot, generalized acceleration and time, okay. The next example here is for damped oscillator, okay. The Lagrangian for damped oscillator is written as e raised to power gamma t into 1 upon 2 mx naught square mx dot square minus half kx square. See, this thing is kinetic minus potential, but this is the relation causing the damping factor, and this is the relation defining the Lagrangian for the system, okay. The next thing is we will study Lagrangian in detail. We will solve questions of Lagrangian. We will study complete Lagrangian dynamics in the next upcoming lectures. It is just the basics, like the factual and definition based basics of Lagrangian. The next thing is generalized momentum, that is pi. X we don't know, x as we showed about xi and xi dot, like qi and qi dot, we have pi. Now this pi, this generalized momentum concept is used in all branches of physics, so we need to be like, we will be watching it in other subjects also, like solid state also, quantum mechanics also, angular momentum, etc, etc. Everywhere this generalized momentum term will occur sometime or someday. Now this it is defined as pi is equal to del L upon del qi dot, that is del L upon del qi dot, which is del qi dot, which is generalized velocity, okay. which is the partial derivative of L with respect to generalized velocity. Okay, generalized momentum is partial derivative of L which is Lagrangian with respect to generalized velocity. It may be linear momentum, angular momentum, or something. This generalized, like we are talking about here, QI. This generalized stuff can be linear one, angular one, or any other quantity. Okay, for example, if generalized coordinate is linear coordinate, the momentum thing will be linear momentum. If generalized coordinate is angular momentum, like angular coordinate, the momentum thing will be angular momentum. Okay, see, we will be studying all of this pretty well in the next upcoming lectures. It was just a This lecture was mainly about the constant ones, and rest was about the definition. We will discuss the Lagrangian in more detail along with many questions in the upcoming videos. Thank you.